Hi, my name is Nicholas Staal, and I'm going to be presenting the final term project for CSCI Principles of Operating Systems. So in this, I'll go over the operating system design, including device-independent I/O, supervisor calls, interrupts, timers, and multi-programming. I'll show a quick demo of the shell, and then after that I'll follow with the demo and explanation of the term project, which was a paint program. For device-independent I/O, a common interface was used where I/O is modeled on files, where you could open, close, put, and get the data from the file. So all devices were using the same interface, including the file in-memory file system. So next we have supervisor calls. There were quite a few supervisor calls, and in general they started as unprivileged shell commands. They would go through a software interrupt routine and enter into privileged mode, and then the actual SVC implementation would run. The shell commands arguments were passed to the implementation as argc and rv. So for interrupts and timers, there's a table there with the individual interrupts that were used in this operating system ordered by priority. The highest priority went to the flex timer, which keeps the current date time. Following that was the UART interrupt for interrupt-driven serial I/O. Next after that was the PDB timer for one-shot function calls. And priority 14 after that was SysTick timer, which was used for the quantum interrupt, and that was used for the scheduler for multi-programming. And the lowest priority went to the SVC, the supervisor call handler routine. On the right there you can see the interrupt vector table where those handlers were located. So for multi-programming, I used a simple round-robin scheduler. There were the common functions for multi-programming like spawn, wait, and kill. For spawn, there was a stack frame struct that was used during initialization where all the individual values could be put in there for when the scheduler caused the new process to run. So in here there are several commands that are pretty useful. To start with, there's a help command, and this will list all of the available commands that the shell is capable of. Another command that's helpful is ls, where you can list all of the file system files and devices that have been created. So these are all the files. There's devices there, as you can see, such as LEDs, there's push buttons. So there's another useful program memory map. And what that will do is it will show all of the currently existing memory segments, which process owns it, whether it's free or not, the size of that segment, and the starting address. Another program is PS, and this will show you the currently existing processes, its state number 2 is ready, where the stack pointer is, the amount of time it's been running, and the process name. So right now we have 2 processes, one is idle and the other one is shell. So a final program I'll show is multitask, and with multitask there are 3 currently running processes. One is flashing the orange LED on and off, roughly about once every half second. There is a second process running, and what that will do is it'll take input from the UART and it'll show it on the LCD. So I'll demonstrate that right now. Right, so you can see that that's showing up on the LCD. And then the third process will take input from the second push button, and it'll show that on the display. So I press it there twice, so you can show that showed up. And then the second process, which is taking input from the UART to the LCD display, is also looking for a control D character to terminate the process in the program. So that is end of the program. So now we'll go back to the PowerPoint to go over the term project. For my final project, I chose to create a simple touch-based paint program on the K70 using the resistive touch overlay. So the LCD RGB display comes with an analog resistive touch panel that can provide coordinates for touch events, amongst other things like gesture recognition. So to use a resistive touch panel, I chose to use the I2C protocol, the integrated circuit protocol, which communicates with the CR touch. And the CR Touch is a resistive touch driver and capacitive touch sensing device all in one. So the features of this program for the user to interact with it are listed here. So you can pick the paint color with the capacitive touchpad and LED combo. So that would be like the orange, green, yellow, and blue lights. For erasing and cleaning the entire screen, you could use the first push button. To switch between an eraser mode on and off, you could use the second push button. And to change the size of what you're painting, so when you create a line or something like that, you could use the analog potentiometer to change your size, like your line size. The program is stopped by pressing both push buttons at once. So I'll give a quick overview of the I2C protocol. So basically in the I2C protocol, there are two lines. One is a clock line, the serial clock line, the SCL, and that's used to synchronize all data transfers over the I2C bus. And there's a second line, and that's the data line where the actual data is sent over, and that's the serial data line, SDA. So the general protocol requires a start and stop signal at the beginning, at the end, which you can see in the diagram. And it requires a device slave address, since more than one device can be listening on the I2C bus. So on the Case70, there's also an accelerometer, which could be listening. So that's an example of where there's a second device listening and therefore the requirement for the slave address. So once again, there were internal registers on the actual CR Touch, and in order to get the X and Y coordinates, basically you would read registers 0x03, 0x04, 05, and 06 in that sequence specifically. If you didn't read in that sequence, you would not get the correct numbers. And in fact, it would just continuously give you the same value until you read the incremental address as shown in the table. So following that sequence of address to incremental address was required. The way it was transferred, basically you would be getting individual bytes. So first they were sending the most significant, then the least significant following that. So to get the actual XY coordinates, you had to then combine those 2 bytes together. Going back to the command prompt, if I type in the command paint, that will start up the paint program. Now it'll show on the UART the XY coordinates. So if I go over and I start changing the XY coordinates, you'll see that those are being updated in real time. You also notice that it is actually painting onto the screen. Color's a little hard to tell, but that is orange. If I use the potentiometer and I increase the size, I'll increase the size that's being drawn. So right now I have the orange LED, and it is drawing in orange. If I want to clear that, I can press the first push button. The screen will clear. I can change the color. Change that to yellow. Now it will draw in yellow. So I can also show the erase feature. So if I press the second push button, that will switch it over to erase mode. Now I can erase. If I want to switch back to drawing mode, I can press it one more time. Now I'm back to drawing. Now to end the program, I'll press both push buttons. Press both push buttons. And we're back to the command prompt.